Okay, it's 4:05, so we'll go ahead and get started now. So, welcome to the first lecture of 6S088 Algorithmic Problem Solving, and thank you for coming today. So, this will be our first lecture, so we'll go over some course logistics, some fundamentals of like data structures and algorithms, and we'll end with a mini lesson on binary and ternary search. So I'll start by introducing the instructors for this class. So we have a small army of them. Some of them are here today. I'm Eric Yang. Um, Eric Su is right here. Wei-Ming Zhou is here. And you'll see a lot more of these instructors later on when they present their own slides as well. So first, what's the point of this class? So we hope by the end of the 2 weeks of this class, you'll be able to learn a lot of really cool algorithms, especially those that aren't really covered that deeply in the normal 612, 10, 6, 12, 20 track. Um, we also hope you'll be able to get better at implementing algorithms quickly and efficiently, since that's also a pretty important skill. And we also hope that you'll be able to do a lot of practice solving real competitive programming problems and applying the skills you've learned. So the format of this class, we'll have class every weekday from today up until next Friday, the 16th. Lecture will be from 4 to 5 p.m. in this room every day, and we'll split them into beginner and advanced lectures. So they'll alternate. Tomorrow will be our first beginner lecture, and the difference is that advanced lectures will generally have a faster pace and build upon the previous day's content. Um, we still encourage everyone to come to like all the lectures, beginner and advanced, since I think it'll be a good like learning experience for everyone. And then afterwards, after every lecture, we'll be releasing about 5 or so problems on that day's topics on VJudge. More details about how to access those problems can be found at our class website here. And after class from 5 to 7, we'll have optional like office hour slash problem solving sessions where you'll be able to work on problems from that day or work together or get one-on-one help from instructors. Next, here's a brief overview of the topics that we're going to be covering. Um, so today is our intro and we'll do a mini lesson on binary search. We'll also, the next 2 days will be over range queries. Then Thursday and Friday we'll be covering trees. Starting next week, we'll be going over graphs, then dynamic programming, and then we'll finally have one day over some tips and tricks on algorithms that we didn't cover in any of the previous lectures. An example of what a beginner advanced split would look like is for range queries. For example, the beginner lecture will be mostly about, for example, prefix sums and like two-dimensional prefix sums, whereas the advanced lecture will be on things such as like segment trees and square root decomposition. Um, as for the programming languages that we'll use, in lecture, we'll mainly be using Python since that seems to be what they teach in most MIT tracks. Um, but don't worry if Python isn't your strongest language, since for our problems in our homework, you'll be able to submit in any supported language, which includes things like C++, Java, and so on. As like a mini reward, I guess, incentive for y'all to come more often, for every problem you solve on the homework, you'll get one raffle ticket. And also every lecture you attend, you also get another raffle ticket. And um, we'll have a raffle at the end of each week. The prizes include things like plushies and merch. And here's an example of some MIT IT merch we have. We have playing cards. We also have like tote bags, t-shirts, things like that. Um, Next, this class is for credit, so you will be graded on a pass-fail. And the pass criteria is pretty straightforward. If you solve a total of 10 problems on our homework contests over all days, you'll pass. And you can track your progress after you make an account as our website. Um, yeah, so that's a bit about our course logistics. Does anyone have any like questions about anything logistics related? No, okay. We'll go on now to an introduction to what competitive programming is. So competitive programming is a great way to kind of like apply the skills you learn in like algorithms and implementation to like real kind of like competition problems. And basically, in competitive programming, you're given a problem of like algorithmic nature, and you have to implement it efficiently and correctly. So usually what these problems kind of look like is you're given like some form of input and you need to like apply some kind of algorithm or like some kind of program to it to output something else. And the thing is, your programs also have to be efficient in that they have to run under a certain time limit and a certain memory limit. Like, for example, a lot of problems require the program to finish within 1 second or use 256 megabytes of memory and so on. Um, I'll go over a brief example of like what a competitive programming problem might look like. So here is the problem. I'll give everyone a minute or two to read over this, and then I'll explain the problem. Okay, I'll give like a brief kind of summary of this problem. So basically, you're given n like batches of cookies, and each batch has like a certain number. And at each time, you want to take two batches and combine them, and then make sure you can like split them evenly between two people. And you want to find out what's like the total number of times you can do this. So does anyone have any kind of like ideas on how you could maybe solve this using code? Yeah. Yeah.
Um, Divide the in an odd actually.
Yeah, exactly. So a good way to solve this is to um, take all your batches and then set all your even batches off to one side and like all your odd batches off to one side. Because whenever you combine two batches, you want to make sure you can split them evenly. So you want like your two batches to sum to an even number. So you can only combine odd batches with odd batches and even batches with even batches. So yeah, you can just like separate the odd batches, the even batches, and then group them together. So a lot of problems also contain things called like sample inputs and sample outputs. So they kind of like give examples for the problem. So in this case, you're given 8 batches of cookies, and the batches contain these numbers of cookies. And so if we separate them into like even and odd, the odd ones have 1 cookie, 3 cookie, 5 cookies, 7 cookies, and 11 cookies. So that's 5 batches with an odd number. And then the even batches have 2, 4, and 6. So that's 3 batches with an even number. Now with the even batches, since you have 3 of them, you have to you can only create one pairing from them. Since you have to combine even batches with even batches, with 3 even batches, you can only create one pairing. Similarly, for the odd batches, since you have 5 of them, you can create 2 pairings for a total of 3 total pairings. They also give another sample with 1, 2, 3, 4. The odd ones are 1 and 3, the even ones are 2 and 4, so you can make 2 batches. So that's kind of like an example of a pretty simple competitive programming problem. Does anyone have any questions about, like any lingering questions about this problem? Okay, we'll continue now. So one thing you have to do in a lot of these problems is to read an input somehow. Like you need to get in, for example, like what the batches of the cookies are in code. And so in Python, the preferred way to do that is to use a function called sys.stdn.readline. What this does is it quickly gets one line of input into whatever variable. So for example, in this snippet of code down there, what we're trying to do is we're trying to get the input of two numbers. So for example, if we input 10 and 8, we want A to be equal to the integer 10 and B to be equal to the integer 8. And how this works is input, we first alias input to be sys_stdin.readline. So then when we call input, we're just getting one line of like input. Then we split it by space. So if our input was like 10 space 8, splitting it by space would give us like string 10 and then string 8. Then mapping it to int gives us like int 10 and then int 8. Then finally we assign them to A and B. And that's how we get like the input 10, 8 into two variables A and B. Similar, if you use C++, using C and C out, you can just add this single line to speed up your input output a lot. Um, yeah, that's a bit about reading input. Are there any, um, yeah, we'll release the slides after so you can reference this as well. But are there any questions right now about how you would do input output? Okay, next, a big part of competitive programming is making your code run efficiently. So one easy way that we calculate how efficiently a piece of code runs is by looking at its time complexity. So in doing that, we only look at the highest order kind of like term and how fast it runs, and we ignore anything else in all coefficients. So for example, if our code took 4n cubed plus 7n squared plus 5 like steps to run, then we drop all like the lower order terms like 7n squared and 5, and also all the coefficients to leave us with a O of n cubed solution. So this means it like grows like a n cubed function. The advantages of this are it's like implementation agnostic, so it doesn't really matter like what your nitty-gritty details are, just kind of like the overall like structure of your algorithm. So it's pretty easy to like calculate during while solving a problem. And it's a good heuristic for asking like, will my program be fast enough and should I implement this algorithm? Um, so are there any kind of questions on like, I guess, competitive programming, runtime, anything we've covered so far? No. Okay, we'll get into our binary search lesson now. Um, So I guess first raise of hands, like who here has encountered binary search at some point? Okay. No worries if you haven't, but basically the standard problem for binary search is you're given a sorted array like this here and some integer x. And you want to find the first element of A that's like at least that number. So for example, if x were 8, then the first element of A that's at least 8 is circled in red. Similarly, if x were 10, the first element of A that's at least 10 is that 11 right there. And one kind of like brute forcey way to solve this, to find the first element of A that's at least x, is to just iterate through your array from left to right until you find an element that's at least x. So for example, if x were 8, you could just start at 1, see like, is 1 greater than 8? Greater than or equal to 8? No. Then you keep going down the array until you find the first element that is at least 8. And that'll give you the right answer, but it's pretty slow since it takes like scanning through the entire array until you find your element, which is O of n time. So we can do faster by using binary search to speed this up. So the overall premise is instead of searching from left to right, we just pick the middle element. So in this case, let's say we wanted to find, again, the first element that was greater than or equal to 8. Then we pick the middle element of our array, and then we ask, is it at least 8? The answer is yes, so we can immediately eliminate everything to the right of it. Since everything to the right of it will definitely not be the first element that's at least 8. Then we've reduced our search space down to this smaller green interval where we can pick the middle element again and ask, is 5 greater than or equal to 8? The answer is no. So we can eliminate it and everything below, since those are definitely not greater than or equal to 8. Then we can keep repeating this process, eliminating more and more intervals until we arrive at a single element as our source space. So we know that this element now must be the first element that's at least 8. Some intuition for why this algorithm is a lot more efficient than the brute force algorithm is that when we run our like left to right search, each time we compare an element, we're only eliminating that single element from our search space. So for example, if we wanted to compare like the first element that's less than or equal to the first element that's at least 8, like we start from the first element, we ask, is that at least 8? No, then we only eliminate that element. Then we go into the next one, and then we ask the same question. We only eliminate that one element. And whereas for binary search, every time we query the middle element, we're eliminating basically half of our entire search space, which is a lot more than the single element for our linear search. So does anyone have kind of like an explanation or intuition for what the time complexity of this algorithm would be? Yeah.
Log-based student.
Yeah, exactly. So kind of like the idea for why this happens is that every time we query a element, we cut our search space down in half. So um, if we keep having, the number of times it takes us to have until we reach one is just like log base 2 of the length of the array. So this binary search algorithm takes us O of log n time instead of O of n time, which is a big improvement. So an example of oh, instead of implementing this like manually every time, what you can also do is use built-in functions from whatever programming language you use. So for example, in Python, there's functions called bisect left and bisect right. So what bisect left does is basically given an array and like some x, it like literally solves the problem we just talked about. So it finds the first element that's at least x. Similarly, bisect right is a bit different in that it will find the first element that is strictly greater than x. So you can use these functions instead of like manually coding your own binary search every time you want to like do something on a sorted array, which is pretty nice. Um, Obviously, there's also a sort function. C++ also has very similar functions. Lower bound is basically bisect left. Upper bound is basically bisect right. And you can view the documentation after we release the slides as well. Oh, so next we'll go over a simple, I guess, example problem that uses binary search. It's called sum of like two sum. And the premise is basically you're given an array of integers and some like target sum, and you want to find two integers in this array that sum to that. Um, so I guess like the naive way is to basically iterate through all pairs of integers and check like does this pair sum to x? Like does the next pair sum to x? And keep repeating for every single pair. But this is pretty slow since um there's O of n squared pairs, and here n is pretty big. So the constraint here is that n is at most 2 times 10 to the 5. With n squared-ish pairs, that's almost like 4 times 10 to the 10, kind of like on the order of that many operations you have to do. As a general rule of thumb, like computers can do on the order of maybe like 10 to the 7 or 10 to the 8 operations every second as a good rule of thumb. So 10 to the 10 is way too much to run in the time limit here. So we need to figure out some way to speed this up. Um, I guess I'll give everyone a bit of time to think about how we could apply binary search to this problem. And I guess once anyone has any ideas, you can just raise your hand and I'll call in. Yeah.
If you could start there and go through each index, and then from there, just like binary search on the remaining.
Yeah, exactly. So basically Yeah, you first sort the array since you need to run binary search on sorted arrays. Then, um, you just iterate through the array. And let's say you're currently at like A of I. Then to figure out if any other element can sum with it to X, you need to find an element that has value X minus A of I. Since if you're currently at element A of I to sum to X, you need another element of like X minus A of I. So to look for that element of X minus A of I, you can simply run binary search. So for example, like you could find maybe the first element that's at least X minus A of I, and then check if that element does equal X minus A of I. So since each binary search will take like log n time, and you're running n of these binary searches, one for every integer in your array, that's a total time complexity of n times log n, which will fit in your time limit and is a lot better than n squared. So yeah, that's one way to solve this problem. This problem is on the homework, so you'll be able to practice implementing this later today. Next, we'll go over a kind of like more sophisticated application of binary search, because it would be a little boring if all I could do with binary search is look through arrays, because you can also binary search on kind of functions in general. So here's an example problem that initially doesn't really sound like binary search, but actually can be solved using it. So you're given an array, and what you want to do is divide the array into k subarrays so that the maximum sum in a subarray is as small as possible. And a subarray in this case is basically just like a continuous like segment of elements in your array. So as an example, with this array and k equals 3, so you want to divide into 3 subarrays. Here's like one possible way you could divide it. So you have the first two elements in the first subarray, the next two elements in the second subarray, and the last two elements in the third subarray. You want to find out, like, you want to find the minimum, you want to minimize the maximum sum in a subarray. So the maximum sum in the maximum sum in a subarray for this split would be 15 from the second subarray. Another way you could split it up is like this. In this case, the maximum sum would be 18. I guess, can anyone see what the optimal way to do this is? As in, like, how could you split this so that you minimize the maximum subarray sum for this example specifically?
First three, one and then two.
Yeah, yeah. So you group the first three in one, then the 10 is its own subarray, then 8 and 2 are in its own subarray. Yes, that's optimal with the maximum subarray sum of 14. So I don't know how you solved it, but at first when I saw this problem, like a lot of it was just based off like intuition. Like, this seems pretty optimal. But like, how can we kind of more formally let a computer solve this? So let's first look at a slightly easier problem. Instead of minimizing the max subarray sum, is it possible to divide these array into k subarrays such that the maximum sum in a subarray is constrained by some value m? So like every subarray must have sum less than or equal to m. So I guess I'll take a minute for everyone to think a little bit about this problem. And if anyone has any ideas, you can just raise your hand. Yeah.
Maybe we just really keep taking, and then like once we hit a point where we can't restart this subarray.
Yeah, exactly. So we basically just iterate through the array and we keep adding to our current subarray while its sum is like less than or equal to m. So we basically kind of like fill up our subarray as much as we can. And then once we're about to exceed m, we like move on to the next one. So as an example, with our array earlier, we can try like, can we divide this into 3 subarrays such that the max sum in a subarray is at most 15? So doing the algorithm, he said, we can keep adding to our current subarray until 14 plus 10, that's greater than 15. So we have to stop and start a new one. Then similarly, we can't add 8 to this subarray since that would exceed 15 as well. So we make this its own subarray, and then we keep going. So we found a solution here that does divide our k subarrays or array into k subarrays with max sum less than or equal to n. So this is possible. Now let's try with n equals 12 instead. So 7, we can add 2 since that's under 12, but we can't add 5 since 14 would exceed our limit of 12. So we make 7 into its own subarray. We also can't add 10 here because that would make the sum 15, which exceeds 12. But then we're left with 2 like remaining elements that we haven't put in a subarray yet. That means that we can't divide this array into 3 subarrays so that the max sum is at most 12. So we now have kind of, oh, and also this algorithm is pretty efficient since it runs in O of n time. You just do like one loop, one scan through the array. But so we've now solved this like easier problem, but how can we like apply it to, I guess, like make our harder problem more solvable? As does anyone? Uh,
Find the here. Eighty subroutine.
Wait, Kurt, sorry, can you say that again?
Try lower values of the deck, minimize.
Yeah, that's a good way to first like solve the problem. So we can just kind of like start n pretty high and then kind of like bring it down until we um like I guess like find the first one that doesn't work, and then we like take the one before that. So yeah, that definitely solves it. Um, I guess is there a way we could maybe speed that up using the binary search we saw previously? I guess um I'll just go through this. So basically, that's basically the right solution plus binary search. So we have a way to check if the maximum sum, if like some value n is attainable. So what we can do is instead just binary search. So we start, for example, with our lower bound at like 0 and our upper bound at like a really big number, and we query the middle. And we say, can we divide into k subarrays so that the max sum is like at most this middle number? If it's yes, we can like eliminate everything above it and like um do the same on our like reduced interval. And if we keep splitting our interval into half, eventually we'll be left with only one number, and that will be like the minimum value of n. So we can, as like a general kind of like paradigm, it's if it's really easy to check if like the answer is at least y or like at most y, but it's like hard to directly find the answer, we can kind of do something like here where we ask like, is the answer at least some number? And if it's no, we like reduce our search space. If it's yes, we like reduce it the other way. And we can keep repeating this until we narrow it down to one single answer. And the time complexity of this, so binary search itself is a log factor. And then each time we check, is the answer like greater than or equal to something, less than or equal to something? In this case, our algorithm was O of n. So our total complexity for finding their answer would be O of like n times log. Yeah, so here is a example implementation of how you could implement this in both Python and C++. We'll do a live coding thing of this problem later, so you'll be able to see like more implementation details. But the general idea is that you kind of have some function that checks like, can you um like is the answer like greater than or equal to x? Then what you do is you start with like an interval, like a pretty big interval. Then every time you like choose the middle, you check like, does this middle value, like is this middle value greater than or equal to x? then you reduce your search space based off of that, just like binary search. And we'll do live coding at the end of the slides. For now, we'll go on to the last topic of the mini lesson, which is ternary search, which is kind of like an extension of binary search onto 3 point, like a splitting array into 3 sections. So the standard problem here is you want to kind of maximize the value of a unimodal function. And a unimodal function is a function that is either strictly increasing and then decreasing, and no two adjacent elements are equal. So for example, the top function here is unimodal. There's like one maximum, it goes up and then down. The second one is as well, but this third one is not, since it goes up, then down, then up again, and it has two like local maximums. So one way to kind of find the maximum value of one of these functions is to just query every single point. This is kind of slow and takes a lot of querying, especially if your like function is real valued. But it's like pretty straightforward. You just like ask every point and then you get the maximum. But is there a way you can do better? You might say like, oh, what if we like binary search? But if we binary search, like let's say we have our interval, we choose the middle point, but then what? So let's say we query our middle point and the value is the black dot there. It could look like the blue function where our maximum is on the left, or it could look like the red function where our max is on the right. So we're not really gaining information by just querying this one point here. Instead, what we can do is query 2 points. So for example, let's split our interval into 3 sections and we query like the 2 midpoints. Let's say it like looked kind of like it was like decreasing among those 2 points. Then one option is it could look like the blue thing where the maximum came before either two of them, and then it decreases throughout. Or it could look like the yellow one where the maximum is between the 2 points we queried. But it can't be the red one. Why is that? Because that would violate the unimodal property of our function. Since if it did go up and reach a maximum there, that would mean our function had to go down between these 2 points, but then go back up again, which is not possible. So we know that our maximum cannot be in the rightmost range if like our points go downwards. So we can cut off that range. And this kind of reminds us of binary search, since each time we like do some point querying, we can cut off a section of our search space. I guess in this case, it kind of looks like we're querying thirds. So like each time we query 2 points, we can reduce our search space down to an interval of 2/3. But we can do kind of better than this, since we're only cutting off like the tail ends. Like if the points were like going downwards, then we know we can cut off the right end. If it was going upwards, we can like cut off the left end. So we can just move our two query points really close together in the middle. So for example, if we have our interval, we take the middle and then like the middle plus one, and then we query these 2 points. If it's like going down, we can eliminate the entire right half of the interval, and if it's going up, we can eliminate the entire left half. So this improves our efficiency to cut down the entire range in half every single 2 queries compared to cutting it down to 2/3. So this is another kind of, I guess, way we can apply like if like finding the maximum of something is hard, but like querying it is a lot easier. Ternary search can also be used to solve this in certain cases where you have unimodal functions. Yeah, so just to reiterate, for ternary search, we must have unimodal functions. For example, these first two, like if you have a unique max, then that's okay. If you have a unique minimum, you can kind of like use a similar logic, but kind of invert the slopes when you're doing your algorithm. But if you have like multiple minima and maxima, then that's not good since our algorithm might settle onto like either local maximum or it could just fail to run altogether. Um, yeah, so I guess does anyone have any questions over the ternary search we've covered so far. Okay. We'll now be doing some live coding. So this is the same problem that we saw earlier, which is like you're given an array and you want to divide into k subarrays such that the maximum sum in a subarray is as small as possible. And I'll basically just, I guess I'll recap the solution. So basically, we want to solve this easier problem of, is it possible to divide into k subarrays such that the max sum is at most some variable m? And we can do that greedily by just like adding things to a subarray until it exceeds m and then starting a new subarray. And so what we want to do now is implement this in code. Okay. So this is the input that we covered in the slides. And first we need to take in n and k, which are the number of elements in our array, and also the number of subarrays we can divide into. So I'll first do our input template. So this redefines input to be sys.stdn.readline. Then we want to read in n and k, and we'll map these, they have to be integers. So then we'll take our line and we'll split it by space. So just to make sure this works, I'll print out n and k. So we read in like the first two integers and then we have the correct values of n and k. Next, we'll read in our entire array here. So we want it as a list. So we'll call it array A to be a list. And then we want them all to be in line with split by space. So what gives us our array A as a list here? Next, we kind of want a function that's able to check whether subarrays such that the max sum is at most m. So what we do is we have a function called check, and it takes in like some m that we want to check. Then what we'll do is we'll keep track of the number of subarrays that we've used. So we start out with one used, and then the current sum of that subarray, which we start out at 0. Then we just iterate through our array. First of all, if this element is greater than m, so like sum at most m, but we have an element that exceeds m, that means that this value of m is impossible. So we'll just immediately return false, as in like this doesn't work. Then we'll check like, can we add this current, wait, then we want to check if I plus our current sum will exceed m. So if I plus, this means that we can't add I to our current subarray, so we want to start a new subarray. Oh yeah.
Possible for you.
Oh yeah, sorry. Is this better? Okay. So if it exceeds m, that means we need to start a new subarray. So we'll reset by adding 1 to the number of subarrays we used and reset our sum to be equal to 0. So this starts a new subarray. Then we add like the current element we have to our subarray sum so we can keep track of like the total sum in our current subarray. So at the end of this loop, what we should get in num subarrays used is like the total number of subarrays that we have if we want to keep all the subarray sums at most m. So if is so if it's greater than, sorry, if it's greater than k, that means in order to keep all of our subarray sums at most m, we've like used too many subarrays, which means it's false. So, but if we've used, first of all, if we used equal to k, then that means we're good since we've constrained all of our subarray sums to be at most n, and we use exactly k subarrays, so that's good. If we've used less than k subarrays, then basically like we can just kind of, how do I say this? If we use less than k subarrays, then we can kind of just make each subarray smaller, and that will decrease our sum in each subarray, which will still allow us to, will just return true. So to, as like a brief check for whether this check function works, we can like try with our this, we saw that m equals 15 should work, so we'll try check 15. That's, so it returns true, so that works. But check 12 should be false. So this function basically tells us, given some m, can we split our array into k subarrays such that, so any questions over this function specifically? Does everyone see why it's a O of n function? It like takes on the order of n time to complete, where n is the size of this array. Okay, so now to solve the entire problem, we just need to perform a binary search. So we'll start by initializing our like range for what our answer could be. So the minimum value is 0, since in the problem we're also told that like every value is at least 1. So kind of like a weak lower bound we can put on it is like obviously our answer will not be less than 0. As for the maximum answer we could possibly have as a weak upper bound, we can just have it be the sum of all the elements in the array. Since if m is the sum of all the elements in the array, the answer will obviously be true since then we'll run our binary search loop. So while low and high haven't converged to a single element, we'll keep narrowing down our range. So we calculate the midpoint element, or like the midpoint value as, so this is kind of like the middle value of a range, and we want to check whether this works. So this means that if check mid is true, that means that max subarray sum, that means that we can attain a max subarray sum of m. So to find the minimum sum the minimum max subarray sum we can attain, we know that it must be our range to be this current value, since we know the minimum will be at most this value. Whereas if it were false, then we know that not attainable. That means that anything that is mid or lower, we can't have max summary sum attain that. So we'll set low equal mid plus 1. So basically, every time we check the midpoint value, we'll we'll cut out half of our search space, depending on whether it is attainable or not. So then at the end, we should have low equal high. And since it should converge to one single element, and then we can just print out either one of them as our final answer for the minimum max subarray sum. And so if we run this, remember from this example, we had an answer of 14. So we should get an answer of 14 here. And yeah, so our binary search does produce the correct output in this case. If you go onto the vjudge place, then you click submit, For Python users, select Python 3, PyPy 3 instead of CPython 3, since PyPy is just like a faster version of Python. Then if we just put in our code here and then we click submit, it will take a while to be judging. And then you can see the verdict here. So this one got accepted, which means it passed all test cases in the amount of required time. The time limit was 1 second here. So binary search was efficient enough to solve this problem quickly. And I guess I'll give you some other examples of like verdicts you could see here. One of them is wrong answer. So for example, if we did like print low +1, this is wrong. So if we try and submit this, you'll be able to see yeah, it'll say wrong answer here. So another verdict you can get is time limit exceeded. So like, for example, what if we just like never terminate this loop? And then we'll try and submit this. This might take a while since it will need to time out on all the tests. But yeah, so here's another I think these are the three like big verdicts you can get. Usually if you get wrong answer, that means maybe like you typoed something, there's might be something wrong with your algorithm or your implementation. If you get time limit exceeded, that means your algorithm might not be. We'll release the slides with this code. Um, yeah. I guess now you all should fill out this attendance form. It's worth 1 raffle ticket, and also you gotta give us some feedback. Yeah. Yeah, for IDE, like I think anything works. If you want, you can also use the same one I used, USACO Guide IDE. If you just look up USACO GUIDE IDE, then it's like one you can pretty easily use online. It supports C++, Java, and Python, and it all runs on your browser, so it's pretty easy to use.
Status behind.
You can use anything you want. Yeah. Okay, so if you haven't already, please go to our website and make an account. We'll keep track of like progress through there. After you make an account, you should also be able to join a VJudge group where we've released our day 1 problems already. Um, yeah, so we'll start problem solving session, I guess, basically now. Um, so you all feel free to like talk, work with each other. If you need help, feel free to just like raise your hand or come up to us, either works. They're also here, they're instructors as well.